All right, so welcome back, everybody. I am going to undo all this so I can keep these rules up because we used those rules yesterday, right? The sum and the difference of two cubes. So yesterday on your assignment, there was one problem that I asked you guys to do, and I say assignment, right? We were asked to factor 8x cubed minus or plus? Plus 216. Now, there are a few cubes. I don't expect you to memorize a bunch of them. I'll tell you, you guys should know that 2 cubed is 8, and probably that 4 is 64. Beyond that, I mean, you can remember as many as you want, right? They go infinitely far, but I only remember like the first 3 or 4 of them, so I wouldn't put a whole lot of stress on that. I do know both of these cubed roots, though. Can somebody help? What's the cubed root of this term? 2. Now, it is worth looking at. Is there anything that we would possibly do first? Before I jump to, like, if I run through my factoring list of stuff. Say it again. So maybe C of 6 cubed, and I think it is. Pretty sure it is. 36 times 6 is 180, and 30. Yep, I'm pretty sure it's 216. There is a greatest common factor here. Now, what is the greatest common factor between these two? 4, you think? Well, somebody, did you say 8? Is that what you asked? I heard 6. I'm sorry. Does 216, is it divisible by 8? Because I kind of bet it is. Probably, right? Now, nobody probably, is 26? 27? Interesting. Nobody probably did this, and that's okay. But I just want to check. If I factor out an 8, it leaves behind x cubed plus 27. Okay, now I have an 8 that's hanging around, and that's all fine and dandy. Do I still have the sum of 2 cubes? Are my numbers nicer to work with than yours were? Maybe. Do you want me to do it with these numbers or with the originals? I mean, we're going to get the same answer. If we do it with this way, let's check. 8. And then I'm just going to let this hang out. It's going to come along every step of the way. Do we know the cube root of this? X. Do we know the cube root of this? 3 times 3 times 3. Yeah. And then what's the sign between them? Plus. Now, these next pieces are so easy to find. All we have to do, and it's the same on every single process, which is why it's an identity, we take both of these and we square them. And I'm just going to say a square goes here and a square goes here. And I'm just going to say squares. Okay, squared, I suppose. Yeah, that makes more sense. And let's just see what that gives us. If we square the first one, it's, this squared is what? X squared. This one squared is 9. And then all we have to do is figure out this middle term. Now, middle term and keep our sign straight, right? Because they do that weird little flip-flop thing. I know that this was a plus, which means this is a minus on this one. How do I get this last term? Multiply these together. X times 3 is 3x. And I was trying to find a way to write that out, but I don't have a nice way to draw the lines. Okay, at this point, we're not done yet, are we? Okay, and we're going to see something, and this is cool that this shakes out. On mine, can you guys find factors of 9 that add up to -3? Can you? I can't. Now, this is okay. This happens sometimes. In this situation, what we see is this one is factored. This one does not factor any further, right? We would have to use a quadratic formula. Now, in yours, it wound up working nicer, right? I think significantly nicer. Where's the issue happening, and what could we possibly change to avoid this issue? Like, and it's okay that it happens. Do you guys understand the issue at play yet? If not, we're going to check it. Okay, do we all agree that I can't factor this any further? Okay, so it seems like I'm stuck, right? Okay, this answer is fine. It's good. We're there. If we didn't do GCF, what would the cube root of this be? 2x plus 6 is our cube root of 8x and 8x cubed, sorry, and 216. And then let's just try the same thing here. What would we have here? 4x squared minus 12x, because I just multiplied this and this, plus. Now, this is the same factorization, and I know it doesn't look like it right now. this one's actually a bit nicer. And it's okay that we have two different approaches through it. GCF is best option 99% of the time. But maybe there are situations where it might make sense to skip it, right? And we're seeing that right now. It's the first time I think that we've actually seen that happen. This one doesn't factor any further, 2x plus 6. But we have this wonderful trinomial still hanging out. Anybody notice something special about this trinomial? It's a perfect square. So as we look at it, let's just check. What's the square root of this? 2x. Okay, so we'll go ahead and do that. So 2x. And this one? 6. So I know that it uses those and gets squared. What's the sign in between them? Minus. In this situation, it was beneficial to hold off on our GCF. Now, they're both correct, and I know, again, it doesn't super look like that, but if we quadratic formula, do you think we'd get the same answers? Absolutely. Okay, two approaches, only time that we've ever seen the GCF not be a huge benefit to us, but it can happen. It's okay if we get here and we have to use a quadratic formula. If we're just factoring, since that was all I was asking to do, both of these are equally acceptable, and I would give you full marks on either. Cool. It's a weird situation, but I'm glad it showed up. All right, for these things, do we want to do more proofs with these, or should we start looking at some other stuff? Okay, I'm going to, you say more or other? Because I just said, didn't really hear, I just heard stuff. Okay, so I still don't quite understand, but I have a challenge for you guys. This is going to seem completely unrelated. What do we name this first section, just because I don't have the notes from yesterday? Polynomial identities. So we got two of them, right? Difference of cubes and the sum of cubes. I would anticipate having to use those. There's one more handy thing that we're going to get to deal with, and we're going to talk about how does one actually go about expanding. And we're just going to look at the most general case. Let's say it's x plus y to the power of n for any n. Now, for these things, if I asked you guys to give me x plus y squared, could you multiply it out? Could you do x plus y times x plus y? Or x minus y, like either way. I think you could, right? And it would take, I don't know, less than a minute probably, even if you FOIL. Could you do x plus y cubed? Would it take more time? Could you do x plus y to the 4th or 5th or 6th? Probably, but eventually, like at 5 or 6, it's going to be such a big problem that it's going to take you 30 or 40 minutes to do, and it just gets grosser and grosser and bigger, right? So what would be very, very, very convenient is if there were a way to simplify this, and it turns out that there is. What we're about to see is a huge idea, and it is so, so helpful in a lot of situations. We're going to find an easy way to expand these, unless you guys would rather do the expansions like this, where you go x plus y times x plus y and do it like 10 times. Anybody want to do 10 of these? Okay, here's the deal. If you want to do it and like do all this distribution and then do it again and again and again, feel free. But I'm going to ask you guys first, can we pick out a pattern? So right off the bat, I just want to know, is there a pattern? And I'll tell you, there is, just so you know. There's obviously going to be a pattern. Okay. In your notes, here's what I would do. I'm going to draw a triangle. Now, I'm going to draw it with numbers in it. Instead, your first number should be kind of over a little bit. I'm going to draw, starting with, I'm not going to make my ones like that every time. I'm going to do a 1. Okay. There's not enough information for a pattern yet. Do you agree? Yeah, you have no idea what's coming next. Okay, but I'm also going to add a 1 and a 1. I'm going to throw this out there and say you still probably don't have a pattern. But I'm going to give 2 more little triangular pieces here, and we're going to see if we can't find it. I'm going to put a 1, a 2, and a 1. I'm going to do one more, and then I'm going to let you guys play around with it for a second. I'm going to do 1, 3, 3, and 1. Do you want, we might have done this as a bell ringer, just like a little sight ahead. But I'm going to give you guys a second. I want you to draw me the next one. I'll give you a hint. It starts with 1 and it ends with 1. I want you to do the next 2 rows of this talking with your neighbors, if possible. Let's try to figure it out. 1, 1, and the next one is going to have a 1 and a 1 all the way over here. Every in between, you should have a number. So you're going to add 3 numbers to this one, and you're going to add 4 numbers to this one. We might have done this in class. I don't recall. Okay. Angel, I don't know where you've seen it. Yeah, it's pretty cool. It kind of looks like bowling. It's not bowling, but it kind of looks like it. I want you to find these 7 blanks. I'm going to give you guys like 60 seconds to see if we can come up with any sort of pattern here. Go. 4, 6, and 4. I agree with that. Okay, now for these, I like the idea of 4, 4, 4, and I see where that comes from. I'm going to add this one more row in white, and I'm just going to add another row below it. 1, 4, 6, 4, and 1. Okay, so maybe I won't even add the next row. How on earth did Kennedy get these numbers? 60 more seconds starting now. If you were a 444 and a 555, let's see if there's a different observation or pattern. Talk it out. So a lot of you guys, I can tell, have like you've identified the pattern. How do I get to the next number? We're just adding. Like, check it out. 1 and 1 make. Okay, 3 and 3 make. 1 and 3 make. 1 and 4 make 5 right here. 4 and 6 make 10. 6 and 4, 10, and 4 and 1, 5. Okay, looking at this, you do not need all these marks. It's just nice to see it. But I could also do the next row, right? Now, for this idea, there is so much living in this. Have you guys seen this triangle before? So some of you have. I have no idea. I might have shown you guys randomly in here one day just as an interesting thing. Or in science, I showed it to you for a different reason. I know exactly why I showed it in science. It turns out, completely different idea here, but they do link. Okay, for this, a couple things. This keeps going, right? We just add them. This pattern has a very important name. This is named after a gentleman by the name of Blaise Pascal, and this is known as Pascal's triangle. Now, there is a crazy amount of stuff that happens in this triangle, and it's awesome, and all of it's super cool. We only get to see little pieces of it. Okay, it seems completely unrelated to what we've been doing. Do you agree with that? Okay, over here, do you guys have room to do a little bit of scratch work with me? Now, I'm going to let my calculator help just so we don't have to spend a ton of time doing only multiplication. But we're going to do a couple things. This is a row. There's a bunch of rows here. So here's a row, and you don't need to draw these, but there's a row, and there's a row. These are all rows that we're looking at. Okay, I'm going to make the claim here in a second what numbers these rows are, and it's going to be weird for a sec, but I want you to help me just at least write stuff down. I'm going to line stuff up with each row. So check it out. If I were to try to expand x plus y, and you guys are going to help me with the first couple, x plus y to the power of 0. It's a weird idea, but what is anything to the power of 0? Okay, so that's it, right? That's the whole expansion. Okay, on this next line, I'm going to do x plus y to the 1. And it seems so odd to do, but I promise we're going to see something awesome happen. What does it give me if I take x plus y to the first power? Now, I'm going to write this a little bit different. I agree with you guys. It's x plus y. But can we agree that this, while we don't write it, is really and truly 1x plus 1y? All right, we're going to do one more, and we're actually going to write several more, but this one might show it up. Some of you guys in here can FOIL in your head. And whether you can or can't, it's fine either way. If you can, somebody feel confident in your ability to tell me what it gives me if I take x plus y and I square it. So x squared, is it 2xy? I'm good with that. Plus y squared. Now I'm going to highlight something again. We don't ever normally write these, but I'm doing it for a very specific reason right now. I'm going to make this 2 look obnoxious also. Okay, as soon as we start doing these expansions, there's something awesome that I want us to start picking out. I have aligned these very specifically with these guys. Do we notice anything about the coefficients? What is the first one's just 1, right? What are the coefficients in front of my variables on this x plus y to the first power. And so it's 1 both times, right? 1 and 1. What about for squared? 1, 2, 1. So check this out. Without doing any of the fancy multiplication and foiling stuff, Lily seems psyched about this, and everybody should be psyched about this because it's a huge time saver. Without doing it, any guess on what the next one will be? So I like the 1, 3, 3, 1. I like that idea, but we need to clean it up more over here. I know it's a 1, but what's connected to it? That should be a cube, I'm sorry. 1x cubed plus, what's the next term? A 1, a 3. Now, here's where stuff gets kind of wonky. For this one, I'm going to help us out with the coefficients first. This is going to be an x squared y. What's the next coefficient going to be? I used 1, 3, 3. This one, it's xy squared. And the last one is back to a 1 y cubed. Now, the powers for these. Normally, it's nice for us because we don't typically have a variable here. We just have the number instead. But we can see that there's something happening. If I look at these x's, notice, I always started with x because it's x first, right? My powers of x, what are they doing? I go 3, 2, 1, and you could do x to the 0 here if you really wanted to, because anything to the 0 is just 1. Are my powers of x counting down? I have x to the third, x to the second, x to the first, and x to the 0. They do count down, right? What do the y's do? If I wanted to write a y to the 0 on that first term, I could. It's just 1. And then I get a y to the, and a y to the, not 1 anymore here. Y to the 0, y to the 1, y to the 2, y to the 3. My y powers are doing what? They're going up instead. Now, we can use this to generalize. We're going to try one more here, and then we'll make the connection back to this triangle. If I wanted x plus y to the fourth. Now, I'm going to use green so I don't have to keep bolding, just with the coefficients. What is going on with my tablet, first of all? And second, what's the first coefficient? 1, and then we'll fill in the other stuff here in a second. The next one? 4. So I know it's going to be a positive in this. The next one? 6. 4. Whoever said 7, I appreciate the idea, but you're way off on this one. 1. Okay. These are the same numbers that show up right here, right? Okay. Now, the hardest part of doing these is making sure we can get the variables right. I'm going to have a biggest power of x going to be what? X to the fourth. Now, if we want, we can do this term by term, or we can just do all the x's and then do all the y's. I think it's more natural to do all the x's and then all the y's because I have these blank spaces. This one got next to the fourth. What does this one get? And this one. And this one. And do you want me to write the 1? Okay. And this one, if it got an x at all, it'd be x to what power at this point? But what is x to the 0 again? It's a 1. So I'm going to include it, and for this one time, I'm going to include a 1 there also. Let's do the y's. The first term is probably not going to have a y, right? Because no matter what, it would just be a bunch of x, x, x. If we just do all the first, we just get x to some power. It is x to the fourth and y to the 0. And then this one is y to the, not 4. We just notice the x's count down, and the y's just count up. It was to the 0. Now it's to the what, Lando? 1. Now it's to the, and to the 4. Now, as we go through, this is incredibly valuable for being able to quickly and easily expand big, ugly things. If you would rather do x plus y times x plus y times x plus y times x plus y, you do you. I'm cool with that. That's allowed. You shouldn't, but you can. Now, for each of these, we're going to make a couple observations, and we're going to tie this back together, and then we'll even see another weird way to get these. And not weird, but just it's odd that it's connected. It's going to be a surprise. Hopefully, like a cool surprise for you, but we'll see. I want to notice something. This is a fourth power, right? If I check this term and I add up the powers on any variable, what do they add up to? 4 and 0 add up to what? So this term, and this is the first time that we've seen x's and y's mixed together, this is a 4th degree term right here because they add up to 4. What about this 2? Huh. What about these 2? Every single one adds up to 4. My combination, my powers, they have to be that way. Now, the weirdest part of this is going to happen right now, and it's strange when we see it. When we talk about labeling these rows, and I'm going to come back and add a few more things to this, we should jot down that note. Note, and we're going to jot down a few things here first, and we'll come back to the triangle. The powers of x do what? And I'm going to say powers of first variable, which is x in this case. As we go through, the powers of x are doing what? So not x and y, just x. What's it doing? 4, 3 is decreasing, or powers of first variable. And I just had var, decrease. What do the powers of the second variable do? Powers of, can I just say second? Increase. Okay, and then the very last thing that we kind of pointed out with this is every term's powers add up to what? Ooh, say that again. N. This, whatever number that is here is what the powers add up to. If we look at the cubed, this is 3, and that's 2 plus 1 is 3, and that's 3. They're all 3 the same way. Every term's powers add to n. Now, this happens on every single expansion that we're going to do. Huge time saver. Okay. We're going to add some stuff in here, then we'll do our quick brain break. Quick-ish. All right. For this, we have a bunch of rows, and I've already made that comment a couple times. Here's a row, and we're going to sneak it over because it's going to be ugly. But we have some rows here. What row is this one? It's natural to say 1 because we typically start counting at 1. Where does our expansion start, though? So this is annoying, but this is row 0. And I get it. I can't do anything about it, but I get it. It's weird, but we use it. What row is this then? And this 3, 4, and 5. And we could keep going, yeah? Like if I wanted to know x plus y to the 6th, you could do this and you could build this triangle. If I wanted to know x plus y to like the 15th, do you really want to build the next 10 lines of this triangle? Probably not, realistically. So our job in here, as soon as we're done with our brain break, is we're going to connect not only that this is super useful and powerful, but we're going to formalize it a little bit more, just so I don't forget where we're at. We are sneaking in and we're following up with this. What we've just talked about, all of this, it has a fancy name. Every single one of these situations, we're expanding a polynomial, and it happens to have how many terms? Each one of this has how many? 2. So they're all what nomials? So we refer to this as the binomial theorem. Okay, the binomial theorem. And there's some crazy stuff that winds up happening with this that we'll talk about here in just a couple minutes. But before we get to that, the question at hand is, what is the best and worst fruit? You have 60 seconds to talk with your neighbor, and then we're going to share a few of them. Just for the record, I know the right answers. Cool. Go, talk it out. See if you guys agree.